CAS is very tricky. Now let's have a look at this integral. Okay, what do you think it might be? Now this is the negative 1 over a square root function. Now that integral should go to, yes, you're right, it's an inverse cos function. So why does the CAS give us a negative inverse sine? Well, okay. Let's see if we can explore two ways in which we can show why that's correct. Now, the first one's an easy one. If we've got a negative of that same integral, like we did there, okay. Well, first thing we could do is just treat that negative as a negative factor of 1. Take that outside the integral and leaves us with this. So then what is that integral of? That is the integral of a negative, of an inverse sine. But we've got this factor of negative 1 there, so it's negative 1 times the inverse sine of x on a. Alright, so that may explain it, but it's not very satisfying. Don't forget the plus c. It's not very satisfying explanation, conclusion. Let's see how some properties of sine and cos and circular functions in general, how we can draw on them to demonstrate it another way. And by doing so, we're going to highlight an interesting thing that the CAS does, which might confuse some students, might confuse you guys a little bit, but it's worth pointing out. So, another important way we're going to demonstrate what happened with the CAS. So, first off, let's think about some properties and symmetries of circular functions. Well, here's one. The complementary, involving the complementary angle. So, if we have cos of pi on 2 plus theta, well, that goes to a negative sine theta. Well, that seems kind of like what we're doing at the moment, where we saw that what should have been the integral giving us inverse cos, in fact, we got a negative inverse sine. Well, this is similar structure to this, isn't it? A cos is equivalent, cos of some angle is equivalent to a sine of an angle. Okay, so let's build upon this. And our goal now is to show that a negative inverse sine of some number, we're going to connect that and show that that is the same as an inverse cos from the point of view of the CAS. So, first off, let's call that angle theta. That is an angle, okay? So, let's rearrange a little bit. I've got my inverse sine of some number is then negative theta, okay? And then from that, let's rearrange again. I'm going to take the sine on both sides, so value A is now the sine of a negative angle, okay? Now, what property do we know about negative angles for a sine function? Well, a sine function is an odd function, so the negative value makes it a negative value on the angle, gives you a negative sine of the angle itself, of the positive value. Aha. Okay, so I now have this, and I'm going to connect that to a cos of an angle. Right there. Okay? Using my complementary angle rule. So that means my value A has to be cos of pi on 2 plus theta. So we're almost there. I'm now going to take the inverse cos on both sides. So I've got now inverse cos of A is actually the same as pi on 2 plus theta. But I'm going to connect that to my very first line. And in my very first line, there it is. I've defined what theta is equivalent to, what theta is the same as. Theta is actually the negative inverse sine of that A. So then that will imply that the inverse cos of some number is almost the same as the inverse sine, but it's being shifted by this pi on 2. Of A. Yep. Okay. Right. So there we have it. There's the true relationship between an inverse cos and an inverse sine. So why is it that CAS kind of seem to give us something different, especially when we're doing the integral? And that's what we've seen here. Okay, we've told that the integral of this negative 1 over the square root, which we know by our rules that's equivalent to the inverse cos. Why does it give it to us as an inverse sine? Negative inverse sine, that is. Well, it does relate according to this relationship between negative cos and our inverse cos and our negative inverse sine. So, an important thing what CAS does has to do with how it treats constants upon integration. So our first integral that we did before, okay, a squared minus x squared dx. Okay, well, we know that then goes to a inverse cos of x on A and, of course, plus c. Okay, that's what we know. So from that, inverse cos is equivalent to what we've got down here. Okay, now I'm going to do that little substitution. So this integral is then the same as pi on 2 subtract inverse sine of x on A plus c as the result of the integral. Now, what's important to make the connection here is that we've introduced this pi on 2 into the result of our integral. But this pi on 2 is a constant, just like the plus c is a constant. And so a funny behavior that the CAS does is it tends to lump the constants together, okay, and then it completely omits the constants from its expression. Doesn't make the constant go to 0. It just kind of cuts it off, kind of truncates it all together, and that's what we've ended up with. We've got, there's our integral, but with no constant. There's no plus c. It's just been taken off. And that's okay from if we were looking for a particular solution and we had to solve for, say, c if we knew a point. That's okay. Or we're solving a definite integral and evaluating that function at different points. Then the plus c, the constant, isn't going to contribute in our calculation. So from that, the CAS is just going to return to us the negative inverse of x on A without any constants. And there you can see the equivalence and how we've ended up with such a result. Okay, it doesn't like, it truly is involving this pi on 2, and that's an important thing. Okay, but CAS is not going to show that when you do an integration because it brings the constants together, even constants we know, like a pi on 2 together with the c, and it omits it completely. It cuts it off. Not very helpful.